Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover the 4 laws of thermodynamics. This content was produced with AI assistance and reviewed by a human instructor. We're starting with foundations, systems, states, and processes. Before we can state any law, we need vocabulary. Thermodynamics is unusual in physics. Its objects are not point particles, but bulk collections, and the laws speak about exchanges across a boundary. Getting the boundary right is half the battle. The system, the surroundings, and the boundary. A system is whatever portion of the universe we choose to study. The gas inside a cylinder, a beaker of water, a star, a cell. Everything else, that is, everything that can exchange matter or energy with the system, we call the surroundings. The boundary is the surface, real or imagined, that separates the two. Figure 2 illustrates the 3 zones of any thermodynamic analysis: the system, the boundary, and the surroundings. Figure 2, a conceptual diagram showing an oval region in the center labeled system, outlined by a bold line labeled boundary. The large region surrounding it is shaded and labeled surroundings. Bidirectional arrows crossing the boundary are labeled matter and energy, indicating possible exchanges. The diagram defines the 3 fundamental zones present in every thermodynamic analysis. Boundaries come in 3 useful flavors. An open system exchanges both matter and energy with its surroundings. A pot of boiling water with the lid off is open. A closed system exchanges energy but not matter. A sealed pressure cooker is closed. An isolated system exchanges neither. A perfect thermos is the standard idealization. No real container is perfectly isolated, but the idealization is essential because the conservation statements of thermodynamics are tightest there. Figure 3 shows the 3 cases side by side. Figure 3, 3 identical containers of gas drawn side by side. The first has an open neck with arrows showing both matter and a wavy heat flow arrow leaving. It is labeled open. The second is sealed, but has only the wavy heat flow arrow crossing the wall. It is labeled closed. The third is sealed and surrounded by a thick insulating jacket with no arrows crossing. It is labeled isolated. Below each container is the corresponding rule. Matter and energy can cross. Only energy can cross. Nothing crosses. Pick 3 objects in the room around you and decide, for each, what counts as the system, what counts as the surroundings, and which boundary type best describes the situation right now. Does the answer change if you wait an hour? State variables and path variables. Some quantities describe where the system is, while others describe how it got there. The distinction matters more than any other in this chapter. A state variable depends only on the present state of the systems. Pressure, volume, temperature, internal energy, and entropy are all state variables. If you know the present state, you know their values. The history is irrelevant. We write the change in a state variable x between an initial and final state as delta x, and that change is the same regardless of which path the system took. A path variable, by contrast, depends on the route taken between states. The 2 important path variables in thermodynamics are heat Q and work W. There is no such thing as the heat of a system or the work of a system. Heat and work are transfers across the boundary, not properties stored inside. 2 processes can take the same gas from the same initial state to the same final state, and yet involve very different amounts of heat and work. Their sum, however, is path independent. That is the content of the first law, which we are about to meet. Intensive and extensive variables. If you place 2 identical glasses of 25 degrees Celsius water side by side, the combined system is still at 25 degrees Celsius, but its volume and mass are doubled. Variables that do not scale with system size, temperature, pressure, density, chemical potential, are called intensive. Variables that do scale, volume, mass, internal energy, entropy, particle number, are called extensive. A useful test: double the system. Did the variable double? It is extensive. Did it stay the same? It is intensive. This split is not cosmetic. Equilibrium between two systems is a statement that an intensive variable has equalized. Temperatures equalize at thermal equilibrium, pressures at mechanical equilibrium, chemical potentials at chemical equilibrium. Figure 4 shows the doubling test applied to a container of gas, distinguishing intensive from extensive variables. Figure 4, two panels illustrating the doubling test for intensive and extensive variables. The left panel shows a single container of gas with three labeled properties: temperature T, volume V, and internal energy U. The right panel shows two identical containers placed side by side, representing the doubled system. The temperature label still reads T, unchanged, while volume reads 2V and internal energy reads 2U. A legend below distinguishes intensive variables, like T, which are independent of system size, from extensive variables such as V and U, which scale proportionally with system size. Equilibrium, quasi-static, and reversible processes. A system is in thermodynamic equilibrium when its macroscopic state variables stop changing in time, and there are no net flows of matter or energy across any internal surface. Strict equilibrium is an idealization, but many real systems are close enough that we can apply the equilibrium framework. A quasi-static process is one carried out so slowly that the system passes through a continuous succession of equilibrium states. In practice, this means the driving forces, pressure differences, temperature differences, are kept infinitesimal at every step. A reversible process is a quasi-static process with no dissipation, no friction, no finite temperature heat conduction, no unrestrained expansion. Such a process can be reversed by an infinitesimal change in conditions, leaving no net trace on system or surroundings. Callan, 1985. All reversible processes are quasi-static, but not every quasi-static process is reversible. Slow heat flow across a finite temperature difference is quasi-static yet irreversible. Norton, 2016. Reversible processes are physically unattainable, but theoretically priceless. They set the upper limits that the second law will use. Figure 5 compares a reversible and an irreversible isothermal process on a pressure-volume diagram. Figure 5, a single pressure-volume diagram with pressure P on the vertical axis and volume V on the horizontal axis. State 1 is labeled at the upper left as P1, V1, and State 2 at the lower right as P2, V2. A smooth blue curve labeled A runs from State 1 to State 2 and is annotated reversible isothermal process. A red dashed staircase path labeled B runs below curve A between the same two states and is annotated irreversible process. The yellow shaded region between the two paths is labeled lost work with an arrow pointing into it. The diagram shows that the irreversible path does less work than the reversible path, and the area between them represents the work lost to irreversibility. That wraps up foundations, systems, states, and processes. Next up, Section 2, the zeroth law, temperature as equivalence. If you found this helpful, like and subscribe and support the channel.